Okay, so we stopped at partial pressures, but I don't have the beginning lecture, but I think those of you who are absent will catch up because this lecture is more important, the second half. So there's a whole section on gas laws that I do, but I won't do it until after this. So you just have to know some information about gases, and you do know that already from Honors Chem. So this is just sort of a continuation of that in like a not so in-depth process. I'm just going to talk about how pressure works. So when pressure is exerted on a container, it's only due to particles hitting the walls of the inside of the container. That's solely pressure. Now pressure can be adjusted due to temperature and volume, but pressure only is equal to the number of hits or bombardment on the walls of the container. And we'll say inside of the container. All right, so if I increase temperature, what am I technically increasing? Always related. Anytime I say anything related to temperature, I'm specifically talking about one thing. Temperature is directly related to? There you go. So if I increase the kinetic energy of the particles, then I have more hits on the walls. Do you agree? Because now it's moving faster, and so there's more bombardments with the walls of the container, so then the pressure would go up. Also, if I increase the number of particles, or moles, I get a greater pressure, right? Because I get more hits. And this also equals more hits. So if there's more moles of substance inside the container, you will get more hits, right? If I decrease the volume of that container, I'll increase the pressure because now I have the same amount of stuff, but in a confined space. So you'll get more hits on the walls of the container. So same stuff, same amount, but increased hits. So the more hits there are on the walls of the container, the greater the pressure will be. Everybody okay with that?
Is that
B? V is in volume. I'm standing in the way, and the camera's in the way. Good. So when I talk about partial pressure, I can talk about the individual pressure of each gas exerting on the walls of the container. So there's this ridiculous law that like any of us could have made up, but Dalton made it up, and he says that this is his law, partial pressure law. That's ridiculous, isn't it? The total pressure is equal to each of the individual pressures. So if I have pressure 1, say it's due to hydrogen gas, that will exert its own pressure because the hydrogen molecules exert their own pressure, right? But then it's also the addition of, say, like nitrogen gas. And nitrogen gas is exerting its own pressure. So the sum of those pressures will give you the total pressure. That makes perfect sense, right? What you may not know is that if I have the same amount of moles of hydrogen gas as I do of nitrogen gas, both of these will exert the same amount of pressure at the same temperature and volume conditions. The type of particle does not alter the pressure because what is pressure solely dependent on? Hits. It doesn't matter who's hitting the wall. It just matters that you're hitting the wall, right? So if I have the same amount of hydrogen gas and the same amount of nitrogen gas at the same conditions, they will exert an equal amount of pressure. So that's what all these bullets say. So partial pressure of a gas in a system is the pressure exerted by that specific gas, right? So P of H2 is the pressure exerted by hydrogen. The partial pressures all add up to give me P total. That's Dalton's law. And 1 mole of one type of gas will exert the same pressure as 1 mole of a different type of gas under the exact same temperature and volume conditions. So that's what I was just explaining, is that they both have the same number of hits on the wall. And then 2 moles of gas will exert double the pressure because you get double the amount of hits. If I put 3 moles of gas in, I get triple the pressure, right? So you get more stuff, you get more pressure. Anybody not sure about pressure, how that works? So this is just sort of fundamental stuff because we're going to talk about equilibrium pressures, and you need to know what pressure means. And then we could also relate that to concentration. So when we relate it to concentration, concentration is how many moles per liter you have. So you could do that in a gaseous environment. I can say I have a certain number of moles per volume. But then I could also calculate the pressure. So we can find Kp or Kc, either or, and plug it into this equation. This equation I thought was given to you on the AP exam, but when we looked earlier today, it is not. but you do have to use it. You have to memorize it. And it seems challenging that you would have to memorize this equation, but it's almost always the same exact answer on the AP exam. And I'll show you what I mean by that in a second. So the first thing you have to recognize is that R is a pressure value. So can you take out your packet of all of your equations? Because you have to identify your R value. There's 3 R values on that packet. So you have an R that says 8.314, and that unit next to it is joules. Do you see that one? You're going to use that for like thermodynamic stuff, and then later on in this year we'll use that again. It's under equilibrium. Actually, I think it's under, on the right-hand side, it says constants. I think that's where your R values are. All right, then the next R value is this one, 0.0821, and the way that you know that you're using that is it says atmospheres. So atmospheres is regarded as a pressure unit, right? And then the other one I think is in torr. So if we wanted to represent something in torr, we certainly could use that to talk about pressure, but for this equation, we're going to use the 0.0821. So that's how you recognize which R value to use as you look at your units, and we want the atmospheres unit. So you would have one of these variables. You would have one for sure because the other one's the one you're finding. These you would know, the temperature would be given to you. Now delta N is the part that's most important. Delta N is products minus reactants. Everything is products minus reactants except for bonds broken minus bonds formed. Like the entire course is always products minus reactants except for bonds broken minus formed. So when you look at your equation, you're going to look for your moles of gas on the product side minus your moles of gas on the reactant side. And they almost always, on my homework, I'm not going to give you it always this way, but on the AP exam, I have not seen a question yet where delta N does not equal 0. They always make it equal to 0. So anything raised to the 0 power is 1. Yep, I wouldn't remember that either, but it is. It's 1. So if I make that equation, the whole thing equal to 1, then what does Kp equal? Kc. Like this entire thing goes away and becomes 1. So then Kp is equal to Kc. So they often do ask this question. I mean, in the 20 years that I've looked at exams and whatever they've issued, I do see this question come up occasionally, often. I don't know what word I want to use. But it's always delta N equals 0. So they'll say, what is Kp? Find Kp, and they give you the Kc value. And then they say justify, and your justification is Kp equals Kc because delta N equals 0. It's pretty much always how the question works. So you do need to recognize that this is the equation. On my exam and on my homework, it will not always be 0. So I'm just trying to make you use the equation, and then you should represent the equation when you're trying to solve. All right, so let's do our first calculation. It says find Kc and Kp for the following system at 427 if the equilibrium concentrations are, and it gives them to me. So this is a simple problem because it's giving me my equilibrium. I'm just going to plug it in. Every time that you start an equilibrium problem, you write your equilibrium expression. What is an expression? Without numbers. So the first thing I want you to do is write your equilibrium expression by just using what you learned yesterday with your coefficients, and it's always products over reactants. So the first thing we're going to do is we're going to use a Kc value. Why am I choosing Kc and not Kp? Yeah, but what does the data in the question give me? It gives me concentrations. If it gave me pressures, I would write Kp. But because it gives me equilibrium concentrations, I think you said that, I'm going to use Kc. So my expression is, go ahead and write it down, and then check on the board when you're done. So for you guys that were absent, it's products over reactants, and you always use the coefficient in the front and put it as the exponent. So if you look at that and see what I wrote there, I'm using the exponent I'm getting the exponent from the coefficient. Did you hear that, Caitlin? Okay.
Is that for the reactions on the bottom as well?
Mm-hmm. So because this is a 1, I just leave it blank.
Yeah.
All right, so now I'm going to go find KC, and I'm literally just going to take the expression there, and I'm going to substitute my values. So I substitute them, and then I solve, and I get KC equals 59. You can jot that down. I trust you can do this in your calculator. We'll do some more in a moment where you can check your calculator skills. So KC equals 59. So let's evaluate what that number means before we move on. So if I have a number greater than 1, just in terms of products over reactants. So every time I write out for myself on an exam, if I'm trying to do like a theory type question, I always write products over reactants for myself, just so that I can consider what the multiple choice question might be asking or the theory question, if I'm not solving for numbers. So I have KC is equal to 59. So this number is greater than 1. Is this products driven or reactant driven? Products. Why? What's greater?
Greater than 1.
What's the numerator, right? That's how you get a number greater than 1, is that the numerator has to be larger than the denominator, right? And if you have a denominator larger than the numerator, you get a number that's less than 1, like a decimal. So you will get multiple choice questions that are theory asking you, and it'll say, is this products driven or reactants driven? Another way that they'll represent this is it'll say product side driven, right side driven, forward reaction is favorable. It might say stuff like that. And then obviously the reverse of this, but there's not really a backward reaction is favorable. But they'll say left side favored and reactant favored. So based on the K value that you get, you determine which piece of your numerator or denominator is larger, and that will be the one that's predominant in the reaction. So because I have a KC of 59, it means that this is products driven, product favored. All right, so back to the question. Now I need to find KP. So I get my expression, and I jot that down. KP equals KC RT delta N. And then you solve, but it's simple. What is KP equal to? KC, because delta N is equal to 0. So you can just throw the numbers in if you want, or you just write delta N is equal to 0. Therefore, KP is equal to KC. All right, next. This is just exactly what I said over here, but now it's just demonstrating it using either KP, KC, or KQ. They're all the same. So I have a value of 0.0184. So I look at this. Products over reactants. I have a decimal. Which side is this favoring? Favoring your denominator, right? And your denominator is reactants. So it is reactant favored or left side driven. If it's, do you know your question?
Yeah, is there like units that we should be using?
Oh, good point. I said this earlier, but I forgot. K, you could work out units, right? Because I could put in like moles over liters and then square it and keep going. We just leave K values unitless. But you could work them out. We just don't have them. It's not typical. And I want to just state this now. I will talk about this again in other lectures. But your K values are they're specifically temperature dependent. The second I change the temperature from 698 to 700, now I get a new K value. So all of your K values are specific to that temperature for that reaction, because you can adjust the K values based on temperature. That's what we'll talk about too when we look at the Le Chatelier's section. All right, so I have a number much greater than 1, so what does this tell me? Product driven, right? Because my numerator then is larger. And again, every time that I do this, I write products over reactants and then I evaluate it. So here's what you're basically analyzing. If you have a K value that's greater than 10, we say it's mostly products. If I'm somewhere in between 1 through 10, I can say not 1, but maybe like, I don't know, a little bit greater than 1. I can't even make up numbers because I'm not sure exactly where it'll fall. But let's say it's like 1.1 to 10, this is somewhat product favored. Not really though, because it's sort of like not far enough along to say that it's truly product favored. Same thing with this. If it's less than 0.1, I can kind of say like, all right, well I'm at 1, but I'm going down to 0.1, right? So somewhere between like, I don't know, 0.9 to 0.1 is probably somewhat reactance. You following what I'm saying? But if it's at 1, that means that, again, K is equal to products over reactants. So if I get a value of 1 here, that means that this must be equal to this. That's not that often that will happen to you, but equilibrium would lie somewhere directly in the middle. That means that you have equal amounts on both your products and reactant side of whatever is present there. So you're really looking for a greater than 10 and a less than 1/10 to say that it's mostly. On the exam, I have seen questions where they say, here's the K value, or they'll ask you to calculate the K value, and then they'll say, determine if this reaction is mostly products, mostly reactants, somewhat reactants, or equilibrium is in the middle. And they ask you to establish that. So you have to really look at your values and see if you can determine it. All right, this is hard because you guys have black and white slides and then you can't even see them over here. But it says, the particulate diagram or representation below describes the following reaction when it has reached equilibrium. Is the value of the equilibrium constant greater than, less than, or approximately equal to 1? So AB is your doubles. All of these are doubles. That's what AB is, okay? This is A, the green ones, and this is B, the blue ones. And the rest of them are all, I can't even draw correctly, combined. All right, so think about that. Is K greater than, less than, or equal to 1? Don't call the answer out. Let everybody think. AB. So how do you determine what K is? K is always equal to products over reactants. I'm telling you, every single time you struggle with a multiple choice question or theory, you write that down. What do you have more of in this particulate diagram? You have more what?
Reactants.
AB. You have more AB, right? How many dashes did I draw compared to how many A's and B's did I draw, right? So I have a lot more dashes up there, which means that I have a lot more reactants. So I put a circle around this and I write big. And then what does that tell me about K? Less than 1. When I do this, this makes perfect sense, doesn't it? Kara, when I said on the last exam that you should write work for that delta G, and you didn't, you got it wrong, but when you did, you got it right. When I tell you to do this stuff, it's because I know how your brains are going to work when you approach these. You're going to look at it and you're like, I have no idea. But if you write down the words product over reactant and you circle which one's bigger, it's almost impossible to get them wrong. So every time you approach these, you write that down. So then K, obviously, is less than 1. Yep.
So if K is equal to 0.9, would that be somewhat reactant?
Sure. Yeah. All right. Calculating equilibrium partial pressures. So it says, suppose you start out with only H2O in a rigid container, and it's in the gas phase, because we know that we don't include liquids, right? All right, so I have some H2O gas in a container, and its partial pressure is 0.784. So the bombardment with the walls of the container give me a 0.784 atmospheres. Everybody following? This is only due to H2O. But eventually, I'm going to produce some H2 and some O2. So it says, what are the partial pressures of each species when the system reaches equilibrium? So because I know that this is a double way arrow, I know how many components will end up being in that vessel. 3, right? It's not a one-way arrow and I only end up with 2. I'm going to end up with 3 different types of substances, right? So I need to figure out what is going to be the pressure of this, what's the pressure of this, and what's the pressure of this. Before you start, is this product favored or reactant favored? Don't call the answer out. What do you look at? JC, what do you look at? No. What do you look at to see if it's product favored or reactant favored? Your K value. Look at your K value. Is it product favored or reactant favored? Reactant, because it's much, much, much less than 1. It is negative 42, right? So you know that it's heavily, heavily, heavily reactant favored. And so that means that I probably will have very little of this being produced anyway, right? We all agree. So if I want to find the individual pressures at equilibrium, I have to do a little bit of algebra. So this is the first time you're going to be introduced to what's called a Rice chart. Because I don't know how much of those will be made. So I call this Rice. Most often it's called ICE, the ICE chart. But I always make you write out the reaction to begin with. So why not call it Rice? Get it? A Rice chart. I didn't make that up. Some other teacher did, and I thought, well, that's a good thing to say. Because you have to write your reaction to start. So we're going to do a Rice chart. So you write your reaction out, and then you start with I. I are your initial conditions that the question tells you. So we only started with H2O in the container, and its pressure is 0.784 atmospheres. You agree? What are the pressures of H2 and O2 when you start? 0, because they're not in there, right? If the question said you started with some of them, then you will. I will give you questions where we start with some hydrogen and some oxygen. And you're going to have to put those numbers in there. But for the most part, they will be 0. All right, the change row tells you how much of the one substance goes away and how much you make of the other substance. Pretend that this was going to completion and we were talking about moles. If I'm talking about moles, let me just say this is like 0.784 moles. I'm just going to throw that in there like that because those conditions are all the same. I'll show you that when we get to gas laws. But this is of H2O. I'm going to say that this goes away by 2 because there's a Roman numeral of 2, right? Like I could say that this is 2 moles to 2 moles of H2. And then I could do the same thing and say it's to 1 mole of O2. So but we're not going to completion. So technically, I have to figure out how much of this goes away, and that goes away by an amount that I don't know, but double the amount, because it's 2x in terms of mole ratio, right? And then I'm forming this, aren't I? So this forms in a ratio of plus 2x, because it's going to go up. And this forms in a ratio of plus x, like 1x, but I'm not writing ones. Everybody following so far? So this goes away. And this forms, but I don't know by how much it goes away because I had that really small K value, right? I really don't know how much of it goes away, but I'm going to solve for it. And then this forms, and remember that graph that I showed you earlier, yesterday, like this one? Well, the slope of this is the same as this, but this slope is like this. Do you follow what I mean? Because there's only 1 mole of this being produced every time 2 moles of this goes away. All right, so that's your change row. Your change row, you just use your moles. In the equilibrium row, you are literally adding I plus C equals E. Write that down. I plus C equals E. You're combining your conditions in your initial row and your change row, and you're coming up, what are the conditions at equilibrium? E stands for equilibrium. So we're going to plug in those values. So I take 0.784, and plus a minus 2x is minus 2x. 0 plus 2x is 2x. 0 plus x is x. These are the equilibrium conditions. That's what E stands for. So at equilibrium, this is what I have. Because it's going away. Right? It's decomposing. Everybody good so far? All right, we need to look at now what is our equilibrium expression. So the problem didn't ask me to write one, but every time I do an equilibrium problem, you should write an expression. So the expression again is without what? Numbers. That's what an expression means, write it without numbers. So I'm going to write Kp is equal to, and remember I used parentheses for partial pressure. So it's products, P of H2 squared times P of O2 to the first over P of water squared, because there's a 2 there. So this is my equilibrium expression. So when I finish this chart now, I have the equilibrium pressures already written down here. I'm going to simply take the E line right here. I'm going to plug those values into the expression. And the problem gave me the Kp value, so now what are you solving for? X, right? So now we're going to try to solve for X. All right, so we plug this in, and we get 2x here squared times x divided by 0.784 minus 2x squared. Everybody good with that? If you were to distribute this, now, oops, let me set this equal to my equilibrium constant. So everybody see where you got that 2.0 times 10 to the negative 42? That came from the question. So 2.0 times 10 to the negative 42nd is my Kp value. So all I did is just plug in the numbers at this point, right? If I were to do this equation and try to solve for x, it would turn into what? Do you know? What kind of equation is this? Starts with a Q. Quadratic. So you would end up with a squared, an x, and then like a whole number, or a number, an integer. So that would be awful. And the AP exam is not really checking to see if you know how to do the quadratic equation. So they will never, ever, ever make you do a quadratic equation on the exam. So what you have to do, there's a few tricks to this. The first thing you have to do is recognize that your value here is so incredibly small, and there's a specific number, 10 to the negative fourth. If it's less than 10 to the negative fourth, I'll show you that in the next slide. We can ignore this little value, because remember I said early on, this is like really reactant driven. Like it's very much going to be all reactants, and there's so little of my products being made. Remember we said that? That's because this number is so incredibly small. So the amount that this goes away is really negligible. I don't really have to take that into account because it's going to be so small, the amount that goes away. So I just ignore it and I cross out that value. Now I can solve for this and make it easier. I had to just throw this little caveat in there before we solve this. If you cannot ignore the x value, and you'll see on the next slide that it has to be greater than 10 to the negative fourth to ignore it. Or I should say less than, right? I guess less than, meaning like it's a much bigger in magnitude negative number. If you can't ignore it, the exam still does not want you to do the quadratic equation. Are you all listening? Because I think I give you a quiz question like this. If you can't ignore it and you have to do the quadratic, it will be a perfect square so that you don't have to do the quadratic. And everything, it'll be all squared. So like, I'm trying to think of an example, like perhaps this is squared, and this is squared. So then what you would do is just like square root this whole thing and square root this whole thing, and then you got rid of all your squares. Do you get what I mean? Everybody hear that? You'll never do the quadratic. So it's either going to be that you can ignore it or you can do a perfect square. I know that you hear me saying that, but then when I give it to you, you'll be like, what am I supposed to do? So that too wasn't there. All right, so now we're going to ignore this x, and you're going to try on your calculator to solve this and get the right answer for x. We have 5 minutes, so let's go kind of quickly here. So in your calculator, if I were you, this is how I would solve this problem. You ready to follow along? I would type in 2.0 times 10 to the negative 42. Some of you will need to hit enter because you have a crappy old calculator. If you don't have to hit enter, then you're in good shape, but some of you have to hit enter. All right, now I'm going to hit times, parentheses, 0.784, and I'm going to square that and close parentheses and hit enter. So now I've just taken this and multiplied it by this side because of algebra, right? Now, what do you do at the top here? At this point, I'm never going to write anything down. But at this point, I'm just double checking with you. It's like 1.23 times 10 to the negative 42. We all have that?
Yes.
All right. That's technically equal to what? 2x squared is what? 4x cubed, right? Because I distribute the square into each of these pieces. So I end up with 4x cubed. I'm sorry, 4x squared times x. Well, this technically is like x to the first, isn't it? And I've taught you so much when we do scientific notation. When you multiply, you add your exponents. So this is technically 4x cubed. Following? So now this is equal to 4x cubed. So I take that value in my calculator, I divide by 4, I hit enter, and now I need to get this x cubed out of there. So at this point, you should have 3.07 times 10 to the negative 43rd. Do you have that?
Yes.
Now, what you do with this is if you have a good calculator, you just go for it. You hit that top, that little hat, except you guys like to call it the caret. You hit that, and you do parentheses 1/3, because a square root is 1/2 power, so a cube root is a 1/3 power. So you're going to get from this, after you do this, you're going to take your number here, and you had it with a 1/3 power. That's how you do a cube root. Square root is a 1/2 power. Cube root's a 1/3 power. So now you should get the answer, and x is, it didn't even put it up there, 6.7 times 10 to the negative 15. Did you get that? That's now equal to the x value, but we're not done. So here is how, this is the last part, and then we're done with this. This is how we're going to check our answers. All right, so I end up with 6.7 times 10 to the negative 15. But that is only this value, x. So P of O2 is 6.7 times 10 to the negative 15, right? But P of H2 is what? 2x. Like, look at your Rice chart that we made. In the Rice chart, the equilibrium line reads 0.784 minus x, 2x, and x, right? Your homework is 1 through 7. 1 through 7. So all you have to do to find your P of H2 is do 2 times 6.7 times 10 to the negative 15. And then to find P of H2O, it's 0.784 minus your 2x, but this is so negligible that it will not change it. So your answer is really just 0.784 atmospheres. Sorry. So your homework really doesn't include this. I put one question with math on it. The rest of it is from like yesterday's lecture, okay? And tomorrow we'll do the rest of the practice problems in class.